by taking the rate law, which shows us a relationship between rate and concentration, and if we integrate it using calculus, we can obtain something called the integrated rate law. This is a useful equation that helps us to determine the concentration at any point in time of the reaction. If we look at the first order rate law, so our overall general form of the rate law is the rate equals K times the concentration of our reactant to the first power, and we integrate that, we end up with an equation that says that the natural log of the concentration of A at any given time, which is given by T, is equal to the negative rate constant times that time plus the natural log of the concentration that we started with. So this allows us, by plugging in time, to figure out what that concentration is at that time. Or if we're given concentrations at the beginning and end, we can figure out how much time has passed. If we plot this, we need to plot the natural log of the concentration of A versus time, and that will give us a linear relationship where the slope is equal to that rate constant. And so this can be a useful way to determine the rate constant of a first order reaction. And the units for K are 1 over seconds. So when our rate is equal to molarity per second, the units for K have to be adjusted depending on the order so that our rate always gives us the same units of molarity over seconds. There is another useful equation that we can look at using the integrated rate law that is essentially finding the half-life, or the time it takes half of the concentration to decrease. And that is equal to the natural log of 2 divided by that rate constant. You may see it represented as 0.693 divided by K, but that 0.693 comes from the natural log of 2. If we look at the second order integrated rate law, where the rate is equal to the rate constant times the concentration squared, and we integrate it, we end up with an equation that says 1 over the concentration of A at any time is equal to KT plus 1 over the initial concentration. Now if we plot our 1 over the concentration versus time, we get a positive slope that is equal to our rate constant and an intercept that is equal to 1 over our initial concentration. So initial, you'll see with a little 0 showing that it's the initial concentration. And so this can be helpful to find the rate constant for a second order integrated rate law. If we want to find the half-life is, or the time that it takes the concentration to decrease by 1/2, is 1 over the rate constant times our initial concentration. And our units for K are a little bit different in this case because it's a second order rate law. We're going to have units of 1 over molarity times seconds. Or you may see it as 1 over molarity times seconds, or molarity to the -1, seconds to the -1. Zero order reactions, we can plot directly the concentration versus the time, and we end up with the negative slope of K. And so this is a constant rate. It does not depend on the concentration of A. If we want to find the concentration at any given time, it's equal to the negative KT plus the initial concentration. And on our graph, you'll notice the intercept is that initial concentration. Our half-life is the initial concentration divided by 2K. And our units are molarity per second when we're talking about zero-order reactions. Let's try an example where we're looking at a reaction. We're told it's first order with a rate constant that's given to us, so that is our K. We are trying to find the concentration of our reactants at 865 seconds. So that is our time. And we're given our initial concentration, which would be our A to the 0 or A naught, A initial. Now we want to pick the right equation. The right equation is going to be based on the fact that it is a first order reaction, which means that the natural log of our reactant is equal to negative KT plus the natural log of the initial concentration. And now we can plug in our numbers and solve the equation. We're trying to find the concentration. We're given that K is 2.90 times 10 to the negative fourth. Our units are 1 over seconds, or seconds to the minus 1. The time is 865 seconds. So we do want to make sure that our units match when we're entering it into this equation, plus the natural log of our initial concentration. So the concentration we started with. Okay, we can simplify our equation, multiplying our rate constant times our time. I take the natural log of our initial concentration. So we get negative 4.04 is equal to the natural log of the concentration at 865 seconds. Now we have to get rid of that natural log. To get rid of the natural log, we're going to raise both sides to the power of E. The inverse function gets rid of the natural log. We take E to the negative 4.04. We end up with a concentration of 0.0175 molar. Now we can double check this because the concentration after 865 seconds should be less than our initial concentration. So the one that we found is less than what we started with, so this does make sense. Determine the rate constant for this reaction. Pause the video to determine your answer. This reaction is a second order reaction, which means that we are going to use 1 over the reactants, concentration of the reactants, times KT plus 1 over the initial concentration of the reactants. So we are told that after 500 seconds, our concentration is 0.001 molar. We're trying to find K. The time is 500 seconds. And our initial concentration is 0.010 molar. So if we simplify this, take 1 over 0.01, we end up with 100. We have to move that to the other side, so 1,000 minus 100 divided by 500 seconds is equal to K, which gives us 1.8. And our units, so the units are going to be 1 over molarity times seconds. So our rate constant is 1.8, 1 over molarity times seconds to make our units work out for our rate.